At the planetary scale, the sheer volume and momentum of the upper atmosphere dictate the behavior of every weather system on Earth. Operational forecasters rely on the 300-200 millibar chart to read this high-altitude momentum, mapping the atmospheric currents roughly 30,000 feet above the surface. The jet stream is a fragmented global current containing jet streaks, intense, localized segments of high-velocity air. While the streak moves modestly, internal lines are extreme. Air parcels accelerate rapidly entering the core and decelerate upon exit, creating a constant mechanical imbalance. Identifying these localized force imbalances is the key to understanding vertical motion and the development of severe storm systems. In the entrance region of a jet streak, air accelerates because the pressure gradient force outpaces the Coriolis force. This imbalance generates an ageostrophic wind, creating upper-level divergence. This textbook 4-cell pattern evacuates mass in the right entrance and left exit quadrants, forcing surface air to rise. Academic models often frame this as a closed, direct thermal circulation, a vertical box where warm air rises straight up into the upper-level divergence zone. In a baroclinic atmosphere, however, this idealized vertical circulation is physically impossible. Forecasters who rely on the two-dimensional straight jet model will consistently misjudge the location and intensity of severe precipitation. Real-world jet streams are rarely straight. When a streak enters a trough, cyclonic curvature takes over. The inertial winds alter divergence fields, collapsing the 4-cell model into a massive 2-cell structure. Here, maximum upper-level divergence and ascent shift intensely to the left exit region. Placement dictates the system's evolution. A jet streak entering the left side of a trough forces it to dig south and amplify. If the streak moves to the right, the system de-amplifies, flattening out as it lifts northeast. Ultimately, jet streak momentum physically carves the planetary wave pattern, determining the depth and movement of global troughs. To find where the air is actually rising, we have to look at a vertical cross-section of the atmosphere, from the jet core down to the surface. Upper-level divergence creates a localized vacuum, causing air pressure at the surface directly beneath it to fall. This drop in pressure triggers the isobaric wind, as low-level air rushes horizontally toward the center of the pressure falls. The southerly component of this air often accelerates to form the low-level jet, pulling moisture into the system. In reality, this accelerating, moisture-rich air bypasses the direct vertical route toward the divergence. It instead interacts with isentropic surfaces, slanted layers of constant temperature that tilt upward toward the colder air. Drawn forward and upward by the exhaust of the upper-level divergence, the massive low-level jet glides up this slanted thermodynamic ramp. This slope ensures that the maximum upward motion and precipitation occur hundreds of miles south or east of the upper-level jet core. Vertical motion follows a slanted trajectory, driven by upper-level exhaust and fueled by lower-level ageostrophic winds. While the low-level jet rises from the south, cold northerly air filters in from the opposite side of the pressure falls. This creates a collision zone where sinking cold air meets the ascending warm moisture of the low-level jet. The resulting tightening of the temperature gradient is frontogenesis. Frontogenesis forces a secondary thermal circulation, which pushes the warmer, lighter air upward with extreme force. This localized circulation stacks with the existing isentropic lift, which compounds the vertical motion and leads to extreme precipitation rates. When the entrance region, the isentropic slope, and frontogenesis align, the atmosphere generates a powerful mesoscale response. In January 1994, Kentucky faced this mechanical alignment. The surface map showed no defined low-pressure system, which initially masked the threat. The 300 millibar chart revealed the real driver. A massive jet streak right entrance region was parked directly over the Ohio Valley. Below the streak, intense isentropic lift drew warm Gulf moisture up the slanted thermodynamic ramp. Severe frontogenesis tightened directly under the jet streak's divergence zone, maximizing the upward motion over the state. These coupled forces produced an explosive result. 1 to 2 feet of snow buried parts of Kentucky in under 12 hours. Analyzing ageostrophic imbalances and thermal slopes on the 300 millibar chart exposes the mechanical drivers of atmospheric vertical motion.